Although you know that Broca's and Wernicke's areas are critical for language processing, in actual everyday life, when you're using language, you're not using language in isolation. It's interacting with the things you're thinking about, the things you're remembering, the world in which you're interfacing, the actions you're taking on. And so all of these different kinds of things will interact with language, which means that in reality, language is distributed throughout the brain. It's not just held in those two language areas. In order to illustrate what I'm talking about, I'm using this figure from the textbook that illustrates Broca's area here in purple and Wernicke's area here in pink. And of course, Broca's area, we learned yesterday, is the motor phonetic area, which means that it's in control of the motor, or actually production of the phonemes, which are the sounds of language. So this is enabling us to create, with motor movements, the phonemes or the sounds of language. Wernicke's area, of course, is the auditory phonetic area, which means we're able to hear, auditorily, hear the phonemes, hear the sounds. So in order to have a conversation with someone, you must be able to produce your own language, as well as hear what you're producing and what other people are producing and understand it. These two things interact with each other. These red arrows represent the interactions across those two areas that are responsible for different aspects of language. If you were to sever the connections between, it would be just as damaging to your ability to process language as if you damaged the areas themselves. Because you have to be able to feed information from Broca's area about what you're producing to Wernicke's area to comprehend what it is you're saying and be able to process and plan ahead your sentences. Similarly, if you're hearing somebody else speak and you want to plan a response, you have to be able to prepare it here and communicate it across to Broca's area where it ends up getting produced. So there is much communication between these areas of the language centers of the brain. However, there are also other arrows, these orange and blue arrows, that go from Wernicke's area out to other cortical regions, or from Broca's area out to other cortical regions, that are responsible for motor processing, acoustics, visuals, tactile information, things like that. So if you wanted to actually do something in addition to speaking about it, if you wanted to say talk about hammering and then actually demonstrate to your son how you hammer, there is going to have to be some integration between the processing of the language, the speaking of the language that you're doing, and other cortical regions, like in the motor cortex of the brain, which is somewhere around this region. You have to communicate between the words you're speaking and the actions you're doing. Similarly, back here at the back of the brain, this is the visual area of the brain. And if you want to be able to speak about what you're seeing, there has to be communication between those visual areas and the actual language centers of the brain. And here, similarly, between the visual areas and the language centers of the brain. So you can see that language isn't happening in isolation. It's interacting with all the other kinds of mental processing that we're doing. Now I want to read a paragraph from our textbook so that you can understand how important these highways of information are. It says, instead of thinking of the brain as an assortment of dedicated processing centers or independent factories, here's another possible scenario, one that is more in keeping with the speculations of Brodmann and Wernicke. Imagine the makers of different products, and they've arranged to share resources and their workers' expertise whenever possible. For instance, the same factory space would handle the production of both fish sticks and chicken fingers, given that they rely on similar procedures. The packaging of many different kinds of goods might take place in another area, bringing together all kinds of frozen foods that go into boxes, including fish sticks and chicken fingers, but also miniature quiches and hamburger patties. In this industrial complex, the production of a specific product wouldn't take place within an isolated factory. Instead, its trajectory from start to finish could be described as a path through the complex, making use of whichever resources were suitable for the production process. Some areas within the complex might be highly specialized, with a very small number of specific products, or perhaps even just one type of product, moving through them, while others would perform general tasks that apply to a great number of different products. One consequence of this kind of arrangement would be that products might have to travel large distances from one area of the complex to another, depending on what specific operations they needed to undergo. From this analogy, you can understand that there are things that need to happen in order to function in our daily life. And some of that might happen in a particular region. There might be vision that needs to happen. There might be motor planning and execution that need to occur. There might be language production, language understanding. There might be other kinds of sounds that need to be processed here. Or there might be higher order thinking that needs to happen up here. But all those things can't happen in isolation. And if you have a particular area of the complex or of the brain that is especially suited to doing a particular kind of task, sometimes you'll find that the brain is able to kind of co-opt that thing, to adopt an area of the brain that's already good at something to do something that's very similar, even though it's not the actual thing that it was designed for. A fun example of this is there's this area near the back of the brain that's called the fusiform facial gyrus. It's an area that's designed to recognize and identify faces. It processes a whole face as a unit, rather than like piecing together the eyes and the nose and the mouth and trying to construct a whole face. It just perceives the entirety of the face together as a unit. But you can also use this brain area for identifying like highly specific trained things. Like if you're a radiologist, you might learn to read x-rays using that particular brain area. Or if you're an animal caretaker, you might be able to determine the differences across the animals in your enclosures that people visiting a zoo wouldn't be able to recognize, but that you would be able, with this very highly specific differentiator, to recognize, oh, that's one giraffe, that's a different giraffe, like, and to recognize who's who. So the point here that I'm trying to articulate is that these different brain areas are highly interconnected with each other, and the connections are as important as the actual centers where the processing is occurring. Indeed, as you can see in this next image, this is called tensor fusion imaging. This is a type of imaging that is similar to fMRI that enables us to look at the connections between brain areas. In fact, what it's measuring is the flow of fluid through large tracts in the brain. These tracts are thousands of neurons that all align with each other to carry information, say, from this area up to the top of the head at this area, and vice versa, to take information back from this top area down to this bottom area, or from this external area here towards the center, or from this area down here in the brainstem out to the cerebellum, or wherever it's going. All of these are tracks within the brain. This represents the interconnectedness of specific brain regions in the cortex that are designed for one specific function, but how those can't work in isolation. The information has to be taken from one area to another. And if you were to disrupt any of those paths along the way, it would be just as damaging as if you were to destroy the actual brain area. Using our factory analogy, you can think that if you took, for instance, like in the processing plant, if you were to disrupt like a supply chain and not allow for trucks to pass to carry their chicken to one part of the factory or to one part of the complex, you would recognize that the end result of that would be just as damaging as if a piece of equipment were to break down and not be able to process the chicken fingers. Why? Because the end result is the chicken fingers don't get produced. It doesn't matter if the reason is because the machinery broke down or because the chicken couldn't get where it was supposed to be. So if you block the roads or if you break the machinery, either way, the thing isn't going to happen. And that same principle is true of language. If you shut down any of the connections, that's just as deleterious, just as damaging as if you were to actually harm the brain regions that are responsible for the processing themselves. Now, the next thing we want to talk about is these two hemispheres of the brain. The left hemisphere is responsible for understanding what was said. We learned yesterday that the left hemisphere is where the language centers of the brain are. These include Broca's area, Wernicke's area, and a lot of integration between the two and between other kinds of areas, and other things that are going on in your life to understand how this language relates with the activities that you're engaging in. But the right hemisphere is responsible for understanding how it was said. It's common in our society to use sarcasm. You know what this means. For instance, if you were to say, "You look good today," that would be taken at face value because of its tone, and you would recognize that somebody was complimenting your looks. But a different tone might say, "You look good today," and that tone would be taken as a kind of a skeptical tone that belies the difference between what was actually being said and the reality in the environment. So somebody might not actually look good, and you might say sarcastically, because their unkempt hair or their unshowered appearance or whatever, you might say sarcastically, "You look good today." The right hemisphere of the brain is the part of the brain that's processing those tonal aspects, how things are being said. This includes things like paralinguistics. Now, in order for us to understand what paralinguistics are, I'm going to reference you to a couple of other words that use the para prefix. Paralegal. This is an assistant to a lawyer. Paraeducator. This is an assistant to an educator. Paralinguistics is an assistant to the language. It's not actual language itself. It's just a support. So you can imagine that in the case of speaking in a sarcastic tone, the tone isn't actually embedded in the words. The tone isn't important in understanding what the actual words to decode meant. Instead, the tone is really taken as context. It's helping us understand the underlying latent meaning, what was being said abstractly. Intonation is what I'm describing right now. That word intonation means the emphasis and the tones that are placed on language. Interestingly, however, there are some languages that require tones to be used in linguistic ways. In English, tones are used exclusively in a paralinguistic fashion. We can say the word so in many different ways. We can say so as the introduction to a summative statement, as in so in summary. You can say so as in why does that matter? You can say so as in I'm disappointed that something happened. So understanding that, we can compare the difference between how we use tones for the word so to how the Chinese would use tones for a word like ma. They have 5 tones. They're similar to the tones that we use, but if you employ the different tones on the word ma, then the word ma means different things. It might mean mother, or horse, or hemp, or to scold, or it might be a question marker. These 5 different tones used in conjunction with the same phoneme, the same syllable ma, and resulting in 5 different words suggest that this is tones used in a linguistic fashion. It's actually embedded in the language. There's no way to dissociate the tone from the word. The tone is built into the word. What that means is, for Chinese, the tone is actually processed in the left hemisphere of the brain because it is a linguistic component of the language. For English speakers, tones are processed in the right hemisphere of the brain because it's paralinguistic. It's a support to the language, but it's not actually part of the language itself. Another example of this is the use of gestures. If you use your hands while you're speaking, the use of your hands can support what you're saying, but it's not an actual part of the language. If you forced yourself to put your hands in your lap and stop moving them around while you were speaking, you could still communicate the exact same thing with the same words that you're saying. The gestures might be helpful, but they're not necessary for the language. So for English speakers, gestures would be processed in the right side of the brain. However, if you spoke American Sign Language and you used almost the exact same movements, but you were using them as words, those movements may be processed in the left hemisphere of the brain because they're actual language rather than mere gestures. The textbook gives this example. There's an image here of the sign to hammer, meaning the verb hammering something. It's very similar to the hand movement that you might make if you were to mime what it would look like to hammer something. You kind of take your fist and you bang something imaginary back and forth onto like an imaginary surface. To pour syrup, again, the verb to pour, is illustrated in this fashion with the hand shape like with the pinky extended and the thumb extended, and you circle it around as if you were pouring something onto a pancake, for instance. The fact that these hand shapes and the movements of them look almost exactly to how individuals would mime these actions when they're asked suggests that you would think these movements would be processed in the same parts of the brain, whether you spoke sign language or whether you spoke English, because you're doing the same things with your hands. But if you speak sign language, you are thinking of this hand shape and its movement as a word, the verb to pour, or this shape to hammer. If you are an English speaker, you are not thinking of it as a word, you are thinking of it as a gesture, and so it's processed in a different part of the brain. These findings suggest that if you're going to learn a new language like American Sign Language or Chinese, that you're going to have to undergo extensive neural re-networking. Your brain is literally going to have to be rewired in order to learn that language, because your brain has to learn that the left hemisphere will engage in aspects of language that were previously only used in the right hemisphere of the brain. Now, I've asserted some facts about the interconnectedness of the language areas with other areas of the brain. But how do we know that this is the case? I want to give you some pieces of evidence that suggest this is true. In order to do that, I have to articulate for you exactly where the primary motor cortex of the brain is and the primary somatosensory cortex of the brain. You need to understand that the primary motor cortex is responsible for executing actions, and the primary somatosensory cortex is responsible for feeling things in your environment, processing what they feel like and their relationships to each other. So you've got sensing stuff with your different senses, and moving with your, executing muscle movement or having motor movement with this region of the brain. Now, if you take a slice out of this section of the brain right here, and you just look at it longitudinally, you will see something that looks a lot like this. It's woven in and out, kind of crunched together. This is the exterior layer of the brain right here, what I'm drawing. That right here is the layer that you're observing right here on the orange. And all the grooves right here that go in and out, those right there are what's depicted as the grooves going in and out, in and out. what we need to understand is that the different facets of your body are represented along this ridge, this primary motor cortex. Right here, you've got all of the things from your waist down, your toes, feet, legs, and trunk right here. After that, you've got some head stuff, some shoulders and arms, then your hands and your digits, your thumb, and then after that, you've got representations of your neck and your eyes, nose, and face. Down here, your lips and your jaw and your tongue. So you can see that it kind of goes from the bottom of your body up to the top, down the arms and hands, and then back to your face again. Okay? Here, I've shrunk this same image down so that we can re-reference it, but I want to talk about a specific study that was done where participants were asked to do certain things with their bodies. They were asked to move their feet. They were asked to move their fingers and move their tongues. And while they were doing these actions, the brain regions that were activated compared to some baseline task were recorded. And you can see that for blue, the foot movements, you have reflected here the activation of the brain exactly where we would expect it to be because of the mapping out here at the peak of the brain, at the peak of that ridge. This right here is that motor cortex ridge on both hemispheres of the brain. Just one side goes like this. That's what we saw on the last slide. On the other side, it goes like the same way. And at the top of the ridge, that's the top right here, the trunk of the body, the leg, the feet, the toes. So if you move your feet, you would expect that area to be activated. The red is the finger movements. You can see on both sides that if you move your fingers, right here where you'd expect it to be, that area is activated. And if you move your tongue, just as we would expect down here, we see that at the far end of the gyrus, that we have tongue movements are activating these regions, and also some parts up here and some back here. When people read action words that were representative of the things you would do with your feet and finger and tongue, like the word kick, step, walk, tiptoe, jump, these words activated these blue regions right here. Interestingly, those map very closely onto the leg and feet region of the gyrus, of the primary motor cortex. If you read certain words that you would do with your hands, like type and throw and write and grasp and poke, these kinds of words activate these red regions that you see here. Interestingly, again, those map onto the same finger areas that you would expect to be highlighted based on the mapping of the primary motor cortex. And finally, when people would read words about their face, like things you might do with your tongue, lick, speak, bite, smile, chew, those facial kinds of words are activating similar but less aligned regions of the gyrus as we saw before. So you can see this is a little further forward on both sides than we saw in the actual movement condition. And that might be in part because they were asked to move their tongue, whereas here they read words about everything on the face. So you can see that there's kind of a little bit of a disconnect between the experimental conditions there. But all in all, it's interesting to see that when you actually do something, it highlights the same brain regions that are highlighted when you just talk about doing those things. In a similar fashion, other research has shown that if you actually move your body first, that you are better equipped to recognize words as real words in some experimental paradigms. An example of this would be if you put your hands in the shape that they would take on if you were to hold a pen, then later on when you're asked to decide in a series of words flashed on the screen if each of those words is a real word or it's not a real word, when pen is flashed on the screen, you are much more quickly able to recognize that that's a real word than you would be if you weren't making this hand shape with your hands. The same thing is true if you were to make a hand shape as if you were holding a knife. Then you were asked if words were flashed on the screen and you were asked to say, is this a true word or is it not a word? When you see the word knife, you would quickly recognize it. If you were asked to process sentences like, he closed the drawer, you would be better equipped to recognize that that was a real sentence and respond to it. If you were also doing something with your body that mimicked the action of closing a drawer, like if you were asked to push a button away from your body in the same kind of motion as closing a drawer, then that would kind of like prime your brain to respond faster and better to that sentence. If you were primed with the word typewriter early on in an experiment, later on you would be quicker and more easily able to recognize that the word piano is a real word. And the reason why that would be is because if you're imagining to yourself a typewriter, it cues in your mind certain movements of your finger that are similar to the movements of your finger that are made when you're playing the piano. You don't even have to move your fingers in those ways in order for your brain to make the connection between the words typewriter and piano. But those words are not connected in any other way except for the movements that they would make with your fingers. Somebody who has Parkinson's disease has deficiencies with planning their motor movements. They're not quite as capable as other individuals are at thinking ahead of the kinds of movements that they want to do and planning how it would be that they could get their body to do those things. As such, when they're asked to recognize whether a word is a real word or not a real word, and the word is related to like a motor planning kind of thing, like walk, step, run, then they would be less capable of recognizing those words as real words. However, if you treat them with a drug that kind of overcomes their motor deficiencies, they treat those motor planning words the same way that they treat other words, as quickly as they do for all the other words, suggesting that it's actually within the muscles of their body that their language deficiencies have arisen from. So taken together, all of these findings suggest that there's a deep connection between the words that you're saying and the movements that those words represent. That indeed there's like an embeddedness of the language in the muscles of your very body, that you can't dissociate language from the environment in which it's being used and from the meaning of the words themselves. So these altogether are examples of kinds of findings that illustrate for us how language is not just held in the language centers of the brain, but is actually distributed across vast swaths of neural networks both in the left and the right hemisphere.